That's the equation of my plan, which means I will multiply 2 times x minus 1, then plus y minus 2 times 1, then plus 2 times z minus 1 equal to 0, and then I will get the equation of the plan directly. So let's see how it's gonna be. So the first step, as I told you, that's the equation of the plan. So I need to evaluate the gradient vector and the position vector. The gradient vector is very, very simple. All I have to do is to differentiate this function with respect to x, differentiate with respect to y, differentiate with respect to z. Those are the derivatives. Substituting at 1, 2, 1, which leaves me with 2, 16, and 2. Multiplying these 3 values by x minus 1, y minus 2, z minus 1. This is what's going to happen. X minus 1, y minus 2, z minus 1. And putting it equal to 0. And that's going to be the equation of the tangent plan, as I told you, at the point 1, 2, 1. Very, very simple and easy to do. So once more, that's mainly the relation that you can find easily of a tangent plan to a certain surface, and that's how it is. The plan is touching the ellipsoid, as you can see. Now I will go to the third point, or the third topic that I want to talk with you about today, which is the extreme points of multivariable functions. In order to evaluate the extreme point of multivariable functions, there is plenty of techniques. The simplest, the one that I'm going to go with you on it. So the first thing to do, okay, as I told you, this is a very important topic in multivariable calculus in general, as it determines the maximum, minimum, and saddle points. The analysis will start with some steps. I wrote those slides in order to help you out in identifying the extreme or the local maximum and the minimum, as you can see. The main steps: compute the first partial derivative of your function. So if I have function in x and y, so I will get partial f partial x, partial f partial y. The second step, I will get the critical points of my function. So I will put the first partial derivative is equal to 0, partial f partial x equal to 0, partial f partial y is equal to 0. I will put them equal to zeros, as you can see. I will solve these two equations together. I will try to solve these two equations together in order to get the components of the critical point. So the solution will be x naught, y naught are the critical points, as you can see. Compute the second partial derivative. So after getting the first derivative, I will get the second partial derivative. The second partial derivative, which is f double x, f differentiated 2 times with respect to y, or f double y. Then the mixed derivative, which is f differentiated with respect to x, then with respect to y, and vice versa. This is gonna be f double x, as I told you, f y double y, f x y, and f y of x. Then I will put them in the Hessian matrix. That's the Hessian matrix. F double x, f double y, f x of y, f y of x. Then I will evaluate the determinant of the Hessian matrix, which is, I usually call it D, as you can see, which is very, very simple. I will multiply the elements on the principal diagonal minus the elements on the secondary diagonal, which is going to be f of xy to the power of 2, as you can see. Based on the value of the determinant of the Hessian matrix and the value of the first derivative with respect to x at the critical points, I will be able to identify if I am a maximum or minimum or a saddle point. So simply, if d is greater than 0 and the derivative of f with respect to x is greater than 0, then it's going to be a local minimum. If the derivative, the determinant is greater than 0 and the partial derivative of f with respect to x less than 0, so it's going to be a local maximum. If in general D is less than 0, then you will have a saddle point. And at the worst case scenario, if D is equal to 0, then your test is inclusive, and we will see what to do after that. This is the third topic of today, which is the discussion of the multivariable functions, as you can see. Okay, as a training, now you have two main problems. I will have to go through them. The first of them, I have the multivariable function x squared plus y squared minus 4x plus 6 of y, and I will need to analyze this problem or to find the extremum of this function if they exist. So the first step is to get the first partial derivative. Let's get the partial derivatives of this function. So I'm differentiating with respect to x is going to be a 2 of an x minus 4. Then differentiating with respect to y is going to be a 2 of a y plus a 6, as you can see. Now I have these two functions. To the second step, I'm going to solve these two equations together, which is really very simple. I will equate the first equation equal to both the first derivative equal to 0 in the x direction, which is going to lead to 2x minus 4 equal to 0. That's x equal to 2. Then 2y plus 6 equal to 0, which means 2y equal to negative 6. That's y is equal to negative 3. So the point or the critical point at this time, it's 2 and negative 3. Now I will have to rush things and getting the second derivative. That's the third step. So I will differentiate with respect to x one more time. It's going to be 2. Differentiating with respect to y another time for the second, it's going to be equal to 2. Differentiating x but with respect to y is going to equal to 0. Or differentiating y with respect to x, which is going to equal to 0. The Hessian matrix, of course, at this time, it's going to be 2 and 2 on the main diameters. So if I want to get the Hessian matrix, it's really very simple. The Hessian matrix in this case, it's going to be 2, 0, 0, and 2. So the determinant of the Hessian matrix is equal to 4. And remark that f double x is going to equal to positive 2, which is greater than 0. Also, according to these two conditions, I will be able to classify my critical point. So the Hessian matrix once more is greater than 0. The f double x is greater than 0. According to my classification, this is going to be a local minimum at this time. Also, another example is asking you to find the extreme points at x squared plus y squared plus 3x over 1. Same steps exactly as you can see. I will differentiate first with respect to x, then with respect to y, putting my partial derivatives equal to zeros, and then I will get this, solve these problems, these two equations. As I told you, this is the first step. The second step, I will put the first and the second equal to zeros. And then I will try to solve to find the second derivative. The second derivatives will help me out in the Hessian matrix, which is going to be 2 and 2, and that's 3 and 3. So D in this case is going to equal to 4 minus 9, which is negative 5 less than 0. And that means the point or the critical point that we have is a saddle point for this problem. So once more, as I told you, that's the Hessian matrix. D is going to be less than 0, as we already evaluated, negative 5, and so it is a saddle point. As you can see for this part, the steps are really very simple. All you have to do is to follow them, but please remark that the study of this part is important. If you didn't study and solve it by your hand, your information will be hazy. So it's going to be difficult on you to memorize them in exams. So it's really very important to resolve these problems. I usually repeat this issue, but unfortunately it's really very important. It's a major thing. Okay, once more, that's another example. 4y squared minus x squared. Do you remember what's the equation of this guy? Which is z equal to y squared minus x squared. Anyone? Yes, you are right, it's a hyperbolic paraboloid. It's a hyperbolic paraboloid. Or the saddle horse as we usually call it. So the first step is y squared minus x squared. In order to find the critical points, I will get the first derivative, which means I will differentiate with respect to x, then with respect to y, which is going to be negative 2x, then 2y. I will take these partial derivatives and put them equal to 0. Once you put the partial derivatives equal to 0, you will have the critical point, which is 0 and 0. That's my critical point. The second step is to use the second derivative test, which means I will need to get f double x, f double y, and the mixed derivative for this function. F double x is going to be negative 2, f double y is going to be positive 2, f x and y is going to be equal to 0, which means those are the results that I'm telling you about. So trying to evaluate the Hessian matrix or the determinant of the Hessian matrix is going to be negative 2, 2 double zeros. The multiplication will be negative 4. That's less than 0, so it's going to be a saddle point. And if you remark, that's the shape, as I told you, it's a hyperbolic paraboloid. And at the origin, you will have a saddle point, as you can see. So it's one of the important problems. And as you can see, the steps are really very simple. And that's the point that I'm telling you about, which is on the other direction, it is a saddle point, as you can see. Okay, those are the Lisbon slides exactly explaining what we did go through. That if D is running from R2 into R, we say that F has a relative minimum, local minimum. At a certain point, if there exists an open ball centered at epsilon such that F is the less than all the points in the neighborhood, that's the definition of the minimum. And for the maximum, F of X node and Y node should be greater than F of X and F of Y. That's an explanation of the critical point. If you get to the point here, then for the open ball, so all the points in the neighborhood of the crown will be less than it, which is the condition for optimality. Same steps: get the first derivative, put it equal to 0, get the Hessian matrix, apply them. If the Hessian matrix is greater than 0 and the first derivative is greater than 0, you will have a minimum. If the Hessian is greater than 0 and the first derivative at your critical point is less than 0, then you will have a maximum. If the determinant of the Hessian matrix is less than 0, it's a certain point. If it's equal to 0, then your test is inclusive. It's the same. The only thing that I want you to keep in mind from those Lisbon slides is the particular case of having a quadratic form. If I have a of x squared to be xy plus cy squared, in this case, if you evaluate the discrement, which is ac minus b squared, and it's greater than 0, and the a is greater than 0, you will have a minimum. ac minus b squared, which is greater than 0, but a is less than 0, in this case, it's going to be maximum. If ac minus b squared, as you can see, less than 0, then it's a saddle point equal to 0, then it is the test is inclusive. And this is a very particular case if your function is ax squared to be xy plus cy squared. And now you can see that the first element, the constant, the coefficients. But for the coefficient of x and y, I will divide it by 2 in order to get the value. I've already shared these slides with you. These two slides are for the proof, the 3 slides, I'm sorry, are for the proof of the result that we pointed out. You have them all with you. I said it previously, so I'm not going to lose your attention going through the details. You have them with you. Okay, once more, I need to determine the relative extrema of the function. The one obstacle that you may face here in some of the problems is that you can find a little bit complicated cases in solving or trying to solve the equations, the first, in order to get the critical points. So once you get the first derivative, the first partial derivatives, and you have your equations with you, equating them equal to 0, you will have two equations, you are trying to solve them together. This is, sometimes it's an obstacle trying to solve these non-linear equations in some situations. But other than that, it's very, very simple. So once more, I want you to compute first partial derivatives. Second, the first partial derivative is going to be 3x squared, as you can see, 3x squared minus 3y, this is going to be 0. For the other side, partial f, partial y, it's going to be, this guy is going to be equal to 0, differentiate with respect to y is going to be negative 3 of x, this is going to be minus 3y squared, okay, for the derivative with respect to y. I will put these two equations equal to 0. So that's the first equation, which leads to x squared is equal to y, as you can see. That's the first information. The second one is negative 3y squared minus 3 of x equal to 0, which means it will lead to x equal to negative y squared. In order to solve these two nonlinear equations, the only thing that we can do is to substitute from one of them into the other one. So I can replace x by y, or I can replace y by x. So what I mean is I can substitute from one of them into the other. So from one, y is equal to x squared. Replace y in the second equation. I will replace y in the second equation by x squared. So it's going to be x equal to negative x to the power of 4. This is what I have. Put them all together in one side. So it's an x plus x to the power of 4 equal to 0. Try x as a common. You will have x times 1 plus x to the power of 3 equal to 0. Which means either x is equal to 0 or x is equal to x cubed equal to negative 1, which means x equal to negative 1 and y is equal to, once x is equal to negative 1, y is equal to positive 1. So now I have the critical points. The first of them is 0 and 0, and the second is going to be negative 1 and the positive 1. So for the critical points, I have two of them, as you can see, 0 and 0 and negative 1 and positive 1. This is the only part that's will need a little bit thinking from you, but as much as you solve the problems, it will be accessible for you. You will have no problem with it whatsoever. Okay? So now I need to test if at these points, if they are maximum or minimum once more. In order to do this, I will have to follow the scheme as you can see. It's very, very simple. Steps. So the first step, I will need to evaluate the second partial derivative. This is the first partial derivative with us. So I will differentiate once more with respect to x, which is going to be 6 of an x. Then I will differentiate y for the second time, which is going to be negative 6 of a y. So if you remark, this is f double x is going to be 6 of an x. F double y is going to be negative 6 over y. Then I will need to get a mixed derivative, which means this is the first derivative with respect to x. I will differentiate with respect to y, which is going to be negative 3. Or vice versa. For the other one, this was differentiate with respect to y. Let's differentiate it with respect to x. Also, it will deliver negative 3, as you can see. Now I can get the Hessian matrix, which is once more, the Hessian matrix is simply f double x, fxy, fyx, f double y. According to this, from the substitution, it's going to be a 6 of an x. As you can see, negative 6 over y. Then instead of x, f of xy, I will put negative 3 and negative 3, and then evaluate the value of the determinant of this function, which is going to be 6x minus 6x minus 6y multiplied in each other, then minus positive 9. Then start substituting. In this case, that's the value of d that I'm going to use. You substitute by the critical points. Let me erase these two values. So if I'm substituting by the origin, it's going to be 0, 0, minus 9, which means it's a less than 0. Once it is less than 0, you will have a saddle point. So for this point, it's a saddle point. I will do exactly the same, but with the substitution with -1 and +1. So all I have to do is to just replace x by -1, y by +1, and see the result. Those are the values. Making the substitution, it will give you 27. In this case, I have d is greater than 0. I will need to find the value of f double x exactly at -1 and the +1. So I'm using these two guys, and I'm going to substitute in this value only, this result. So replacing x by -1, it's gonna equal to -6, which is less than 0. So once it is greater than 0, but f double x is less than 0, it means you have a maximum point, as you can see. So as I told you, this is how you will have your local maximum. This problem is, and the previous ones are really very simple. It's a systematic process, 1, 2, 3. So once more, for Seda, in order not to feel afraid, the first step is to get the partial derivatives. The second step, put the partial derivatives equal to 0. You will have equations. Solve them together. You will get your critical points. Step number 3, get the second partial derivatives. Multiply them together in order to get the value of d, which is the switch that will tell me if I'm maximum or minimum or saddle point, or the system or the test will fail. Okay, so it's really very important, as I told you. Please, once more, try to resolve these problems using your hand. The only obstacle or the little bit twist that will need more focus from you is how to solve the nonlinear equations, they usually by substituting from one into each other. In this part, of course, we are in sheet number 6 for you to know, and I've tried to solve as much problems as possible from the previous parts plus the new parts. So once more, in this lecture, until the time being, we already did go through 3 main parts. The implicit function theory, that's the first part. Then we went through the directional derivative, how to find the directional derivative of a function. Number 3, the extrema analysis, or the local extremum, maximum, minimum, and saddle point. Those are the 3 main points. Of course, we have the differentiability tests with us, the continuity tests with us, because they may appear in the problems. They are all connected to each other. As I told you, I solved a lot of problems on this part, and I sent you the PDF earlier. Don't be afraid from the problems. Give yourself a chance to read well, then try to solve. So for this problem, he wants you I will try to solve a couple of them, because I want to conclude our lecture today and pass through plenty of problems at the same time. So I will try to go through some problems quickly. Others I will spend time trying to solve them with you, or to go the steps with you, and you have the PDF completely covering all of this. In this problem, he gives you f of x and y. It's a function running from R2 into R, as you can see, where, as I told you, don't panic. It's an f in x, y, sine x, cosine y. And he wants you to determine the directional derivative of f in the direction of w. So I'm going to evaluate the directional derivative in this problem. Okay, where w, okay, is u and v, belongs to R2, which means it's a general vector. Represents a generic unit vector. Oh, he told me it's a generic unit vector. We don't need to check that if this vector is a unit vector or not, because he already announced this for me. Okay, now continue. If I want to evaluate this, yes, Ms. Seda, you are right. The directed derivative of f at certain point x node, y node, in the direction of a vector, it's very, very simple. All I have to do is to get the gradient vector of f at the indicated point, then I will multiply it as a dot product in the vector w that already is in normal form. So all I have to do right now is to get the gradient vector. How to get the gradient vector of this function? It's very, very simple. So the gradient vector of f is simply the partial derivative of this function with respect to x, then the partial derivative of this function with respect to y. That's the gradient vector. So start differentiating with respect to x, which is gonna leave you with cosine of an x, am I right? Cosine of a y. Differentiate with respect to y, yalla. So it's gonna be sine negative of a sine of an x for the first, but trying to differentiate cosine y, it's gonna be negative sine y, as you can see. Now I have the gradient vector. All I have to do is to multiply this value by the value of u and v. And so the final answer is gonna be the directed derivative of f at x node, y node, in the direction of w. It's gonna be cosine of an x, cosine of a y times u, minus sine of an x, sine of a y dot v. That's it. Because once you do dot multiplication, you will multiply the first component by the first component and the second component by the second component. It's very, very simple, as I told you. But the way it is written by, and if you didn't solve using your hand, it will look complicated and it will make you afraid or not comfortable trying to solve these problems. So once more, as I told you, شايف حركة جديدة. You want you to consider the real function f of xy sine x or sine y. So once more, all I have to do, I want you to remember the directional derivative. This is the main formula, which is the gradient dot w. Simply, I will get the derivative of this function, cosine x, cosine y dot u, minus sine x, sine y dot v, as we did. Okay, exactly. If you need a specific problem to check, all I have to do is to substitute by x node, y node, as I told you, and that's the solution. This is also, all of this are just to make you remember the directional derivative, because previously this was solved in another lecture, okay? So that's just a quick reminder for you. So once more, if I want to solve, all I have to do is to get the gradient vector. As I told you, cosine x, cosine y, minus sine x, sine y. Then I will multiply them by the vector w, which is u and v. That will leave you with cosine x, cosine y times u, minus sine x, sine y dot v. That's the result. For a specific value, for another problem, if you are given specific values, he will give you, for example, if xy is pi over 4 and pi over 3, and the direction of w is 3 over 5, 4 over 5. Remark, yes, that's a good remark. This vector is a unit vector. Yes, I can check that it is a unit vector really by getting the norm of this vector. Say that, do you remember how to get the norm of a vector? Which is simply the square root of the first component, am I right? Plus the second component, which is gonna equal to 1. So it's a unit vector. Okay, so all I have to do is to find cosine pi over 4, this is pi over 3, and the value of u is 3 over 5, sine of an x, same way like at pi over 4, this is at pi over 3, and the value of v is 4 over 5, direct substitution. Now I will get the value. So once more, as I told you, the direction unit vector is gonna be, this is equal to 1, so I'm checking the unity of my unit vector. The values at pi over 4, those are the values of cosine pi over 4 cosine pi over c, the values that I'm going to substitute in. Just a direct substitution, and you will get the value of your directed derivative in front of you. It's really a very simple problem, as I told you, but the main issue is to try to solve it by your hand as we did before all of this. Okay, now for this function, he wants you to consider the following function, which is 3y x minus a piecewise function. You know that we are big fans of piecewise functions, because usually piecewise functions are the more practical case in describing certain physical formula, phenomena or engineering phenomena. Okay, so he's giving you a function which is defined when xy doesn't equal to 1 and 0, you can use this kernel, and if x and y equal 1 and 0, then the result will be 0. He wants you to study the continuity of f at a certain point, and that's an old topic. And if so, consider the vector, that's the vector, study the existence of the directional derivative at 1 and 0 on this direction. So you have the function, you have the direction, okay, and so on. So it's very, very simple. If I want to just prove the continuity at 1 and 0, all I have to find or to prove is that the limit of the function exists and is equal to the value of the function in the definition. The definition states that the value of the function is equal to 0. So all I need to check is to have the limit xy approaching 1 and 0, and it should equal to 0. So once more we get back to the limits. How to check this limit? If you remember, I have plenty of ways to check. Either by Cauchy, okay, because I have the standard there, which is epsilon and delta, or changing into polar coordinates and see if it's gonna tend to 0 or not. So if I want to change to polar coordinates, simply I will use x equal to 1 plus r cosine theta and y بيساوي r sine theta, because if you remark, I'm approaching 1 and 0. Okay, so I'm approaching 1 and 0. This is the coordinates of the center of the open ball that I'm using. So I will use x equal to 1 plus r cosine theta, and this is in the parametric part. Remember, all the topics before our first midterm, they are tools with you. You are not, in the second midterm, you are not going to be asking about certain one of them, okay, in specific, but you may need the knowledge, okay? So I have the names of the shapes with me. I will need them through the next slides. Also, I have the huge tool of parametric representation or playing with the various coordinate systems that we had previously, okay? So now I know using the parametric representation, and which is very, very simple, very close to the polar coordinates in this case, r and theta, okay? I will use x tends to 1 plus r cosine theta and y r sine theta. If I'm using this, which means that x minus 1 is gonna equal to r cosine theta, so I can replace this guy by r cosine theta, and I can replace y by r sine theta, which is make a huge difference in the denominator. Same will happen in the, in the denominator. Same will happen with the denominator. So once more, that's the substitution will equal to r. Now all I have to do is to start substituting. Instead of having 3y, it's gonna be 3r sine theta. This is gonna be just only r cosine theta. And the denominator after substituting is equal to r. So if you remark, Ms. Seda, I will eliminate r with r. So I will have 3r sine theta cosine theta. Okay? Now I can take the limit when r tends to 0, which leads to that the limit is equal to 0. Now the limit equal the definition. So the function is continuous. Okay? So at the time being, the limit exists and equal to 0 from all directions, because we have proved this through r. There is another method, of course. I can use the directed method, And after the directed method, I can use Cauchy, which is epsilon, if you remember. For each epsilon greater than 0, there exists the delta. Then I will use the kernel and to try to manipulate using the inequality. Do you remember those steps? And it's going to give you the same result, okay? So once more, now I have the function is continuous. Now I will need to go through the directional derivative. Since my function is a piecewise function, I will use the definition or the formula for the directed derivative. So now I will get partial f partial x at 1 and 0, partial f partial y at 1 and 0. To get the partial derivatives, in this case, I will need to use the partial derivative by limits, because it's a piecewise function. It's not the function in all the domain. If you remember, it's going to be partial f partial x, limit 1 plus h in the x direction and 0, minus f at 1 and 0 over h. I will take these values and substitute in this function. So I will replace x by 1 plus h and replace y by 0. So once you replace y by 0, these values are going to equal to 0. So the first partial derivative exists and it's equal to 0. And in a similar manner, this is what's going to happen. Once you start substituting, it's going to equal to 0. Same way will happen with the partial derivative in the y direction. In the y direction, this guy is going to be 0, but that one is going to be 0 plus h. And then making the substitution also, once more, here we go. So that's the value. Partial f partial y at 1 and 0, it's going to be exactly as I told you. Making the substitution, x is going to be 1, and this is going to be 0 plus h. So if you take those values and start substituting in the main function, replacing x by 1, it will make this part equal to 0 times h, so it's going to be 0 once more. So the partial derivative is going to equal to 0. Now I have the partial derivative in x and y is equal to 0. Which means that the gradient vector of f at 1 and 0 is equal to 0 and 0. Which means multiplying this guy by any other vector